So we're going to continue the related rates that we started with the part 1 series. And in related rates, remember that what we're doing is we're talking about how different dimensions, different relationships between two things, how they interact with each other, and a rate has to do with a time derivative, how quickly or how slowly something's changing, and a rate says we're going to take a time derivative of everything. So let's start with another one of the very often used problems where you have something falling out of a container or off a conveyor belt, out of a trough or something, and it's going to form a cone-shaped pile underneath whatever it's depositing out of. So it's not going to be, of course, a nice straight side because things that are falling out of a container aren't nice and straight. So this would be the altitude, and this would be the distance across the base. All right. So it says sand falls from the end of a conveyor belt and forms a conical pile on the ground below. The vertical height, which is this part right here, h, of the pile is always 2/3 the diameter of the base of the pile. How fast is the radius increasing when the diameter is 12 feet and the volume is increasing at the rate of 24 cubic feet per minute? So again, like before, you have this ongoing process. Something's taking place. At some point in this process, you're going to take this little snapshot and try to analyze it at that point where everything sort of freezes. Now, in this case, you know you're dealing with a volume because one of the pieces of information it gives you is 24 cubic feet per minute, and cubic inches, cubic meters, cubic millimeters. Cubic is a volume. So the volume of a cone is 1/3 pi r squared h. And hopefully by this time your teacher has let you know whether she or he expects you to memorize these various volumes and areas, circumference, surface areas, if they're going to give it to you as a formula list, or if they're going to let you bring in a sheet, sometimes called a cheat sheet, though it's not cheating if your teacher lets you do that, of various information for use on the test. So let's assume that one way or the other you have access to this volume formula. Now, to do a rate of anything, you're going to take a time derivative. So if we take the time derivative, we would have dv dt is equal to 1/3 pi, because those are just coefficients. And r squared h is the product, so it'd be the first times the derivative of the second plus the second times the derivative of the first. Now, if you look at this, how many unknowns are in here? You would have to find a value for r, that's 1. Then dh dt is 2. H is a third one. R we already have. And dr dt is 4. So there's 4 pieces of information you would have to acquire. And that's way too many for the information that we are supplied. So let's look at what's being told us and see if we can do anything about that. The only information they give us is the vertical height is always 2/3 of the diameter. Okay, so h is 2/3 of the diameter. And how fast is the radius increasing? So that's dr dt. When the diameter is 12 feet, okay, and the volume is increasing at the rate of 24 cubic feet per minute, and that's dv dt. So it's asking for r. And this is a relationship between h and d, but isn't h, in terms of d, something we can manipulate by saying the diameter is twice the length of the radius, right? So h is 4/3 r. Now this relates h and r, so we could go back up into here and either substitute 4/3 r in for h, or from here we can say r is 3/4 h, and we could substitute that in and get everybody in terms of h, right? So if it had asked for dH dt, I'd say let's change everybody to an H. But right here it says how fast is the radius increasing, which is dr dt. So I'm going to try to get rid of the H and substitute in an equivalence for R. So H is 4/3 R. So you have this part that we were going, okay, this is going to be too big of a problem for us to do a time derivative. So let's back up. Try again with something a little simpler. We still have 1/3 pi, but now what we have is r squared times 4/3 r, because we substituted in for h. So the volume would be 4/9 pi r cubed, right? So that helps us with our variables, right? Now we're going to take the derivative, and we would say dv dt is 4/9 pi. We would bring the 3 down, take 1 off the power, loop back in, and take the derivative of the inside. Y'all doing okay? And then this 3 reduces that fraction, and you'd have 4/3 pi r squared dr dt. And I'm thinking I'm kind of satisfied with this. Let's go back up here and see what we can find. So it says, how fast is the radius increasing? All right, now that's dr dt, which means this is what we're expected to find. I have to have values for r and dv dt, right? So that's what we got. dv dt is this 24 cubic feet per minute, right? That's this part right here. And it says the diameter is 6 feet, and I'm looking for r. Well, r is half the diameter, so half of 12 is 6 feet. Okay? So dv dt is 24 cubic feet per minute. And this is 4/3 pi. R is 6 feet squared dr dt. All right? So when you divide this out and clean it up, you're going to divide both sides by 36 square feet. So that square feet's going to take out 2 of these right here from the cubic. And when you clean it up, it ends up being 1/2 pi feet per minute. Now, this is if you want an exact value. But if your instructions say to round it off to, say, 3 decimal places or something, you can run this on your calculator, and rounding it off, you will get 0.15 feet. Having trouble spelling today. Feet per minute. All right. So this one is approximate. If they don't tell you to round, they're expecting you to leave it right here. Unless your teacher's done something that says, for the purposes of this class, we're always going to round to, this point. Then that would be a different story. Now, let's consider the same thing, a little bit slightly different information. And again, we have sand falling off a conveyor belt, forms a conical pile. The height is still 2/3 of the diameter of the base, which is still 2/3 times 2r, which is 4/3 r. Okay? And it says how quickly is the volume of the pile increasing when the base diameter is 6. Now, this is not the same exact problem as before. In this case, the diameter is 6, so that would make the radius 3 feet, right? And dr dt is 0.25 feet per minute. Okay, now again, this is a volume, so the volume is 1/3 pi r squared h. Now, if you want to, you can walk through the same math that we did before, where we said h is equal to 4/3 r. Substituted it in right there. And after we cleaned it up, we got v is equal to 4/9 pi r squared. It's supposed to be v. Now, how about cubed? All right. Now, so when we take the derivative of this with respect to time, we have 4/9 times 4/9 pi times 3 r squared dr dt. So it's 4/3 pi r squared dr dt. And when you substitute this in, r in this case is 3 feet because we're not doing the exact same problem as before. Squared. And in this case, they're asking you to solve for dv dt because it says how quickly is the volume increasing. So dr dt is 0.25 feet per minute. And this would be dv dt. So when you straighten this up a little bit, it's 3 pi cubic feet per minute. That would be the exact. Or if you round it, it's something like 9.42 cubic feet per minute. So this is the approximate, and this is the exact. All right. Wasn't too bad after you set up the first one, right? Now, a lot of times one of the favorite problems to have y'all work on is something that has to do with like a light. It could be a street light. It could be a spotlight. It could be anything that casts a shadow. And then they'll have you either imagine yourself walking toward it or walking away from it, and the shadow would increase or decrease. Something just fell off my desk. I know y'all are like, okay, what is she doing? All right. So you can always ask. Now, here you go. All right, it says a bright flashlight is dropped on the ground and shines its light on a vertical wall 15 yards away. If a person 6 feet tall runs from where they dropped the flashlight towards the wall at a speed of 1.2 yards per minute, how quickly is the shadow on the wall shrinking when they are 5 yards away from the wall? All right, so that's a lot of words in there, right? But basically what you're dealing with, and I think you know by now that I'm not the best drawer in the world. I'm just grateful you can get an engineering degree without having to be a good drawer. That might have been a problem. All right. Most everything you have to draw needs a ruler. Okay, so here we go. Now, you just got to have fun where you can. It's not enough fun in the day. All right. So down here is your flashlight, right? So you've got your light shining, from down here. You drop it, you run off. This right here is the person, this vertical first height. Notice that everybody's in yards. Okay, you're 5 yards away from the wall, 15 yards away from the light from the wall, but the person is 6 feet tall. So this is not 6 feet. Okay, this is not 6 feet because that's a mix of units. Okay, so 6 feet is 2 yards, right? So this is 2 yards. Be careful with that. All right. And this value, let's call it y, is how your shadow is going to change that far up the wall, right? And then now let's start off with a kind of a concrete example. So this says that you are 5 yards away from the wall, right? And it says originally the flashlight was dropped 15 yards away, so this is 10 yards. Now, I want to talk about this for just a second. So the total distance from here to here is 15, right? So if the total distance is 15, and if this was 4 yards instead of 5, this would be 11 on this side of that vertical line, right? If this was 6 yards on this side, this would be 9 on that side. So whatever this distance is right here, this distance is 15 minus whatever that distance is, right? So this one is 15 minus whatever the distance from the wall is, right? So 15 minus this one is how you get this other side, right? So I need sort of a generic case. And sometimes it helps to come up with a specific case first, as long as you remember that you need a kind of a generic case to set up your equation. All right. So if you know that you are X yards away from the wall, this end is 15 minus X, right? 15 minus whatever X is. All right. So let's go back up here and let's think about similar triangles. So 2 is to 10, because that's this first baby triangle. So 2 is to 10 as y is to 15. That would be the bigger triangle. This one and this one. All right. So when you cross multiply, you get y is 3. Okay. Now, let's set up our generic kind of an equation. So 2 is to 15 minus x as y is to 15, right? So the y is to 15 is the same. But now what I'm saying is that may not be 10. That may be just 15 minus whatever x is. So I'm going to change that to 15 minus x. Because the whole total distance of 15, this total distance from here to here of 15, the total distance doesn't change. The only thing that's changing in here really is how far this person is running from the light, and of course y is going to change as a result of that. All right, and the person's height's not going to change. So let's try to cross multiply this, and we would get 30 equals 15y minus xy. And that looks like a reasonable equation, right? I could take the time derivative with that with respect to t. So the derivative of 30 with respect to anything is 0. Okay, then you'd have 15, and the derivative of y with respect to t is dy dt. Okay, this next part is the product rule. So you would have the first times the derivative of the second, because the derivative of y with respect to t is not 1. Okay, it's dy dt, plus the second times the derivative of the first, and the derivative of x with respect to t is not 1. The derivative of x with respect to x is 1, but this is dx dt. Okay, doing all right so far? You should always kind of stop and look at it and go, okay, I'm still hanging in there, right? The nice thing about a video is if you're going, wait, what did she just say? You can, back it up. So I'm going to factor out dy dt, and that would be 15 from this first term minus x from the second term. And that would leave you minus y dx dt. And if you're trying to figure out where the minus came from, it went here. Okay, so let's see what I've got. 0 equals. Now, what is it exactly they're asking me to find? Okay, let's go back up here and it says, how quickly is the shadow on the wall shrinking? Okay, so what they're asking you to find is this one. So that means somewhere in there must be the information for X and the information for Y at that instant and dx dt. Okay, so let's look back up here. All right, X is this distance right here, which is 5. Y is this distance right here, which at that moment in time we said was 3 yards, right? All right, so let's go back down here, see where we can get. So dy dt is 15 minus x, which is 5, minus y, which is 3, dx dt, which they said he runs or she runs with 1.2 yards per minute. All right. And when you solve this out, dy dt equals 0.36 yards per minute. Okay. One more. All right. Another one you see all the time. I'm not sure why I've even seen this in engineering books. Okay. So, and I'm, as you know, a very bad drawer. So here's my boat. Okay. Sitting on the water. And there's a rope right here. And somebody is drawing it in to a dock through a ring right here. So there's a person standing down here and they're pulling in this rope. But what all of our dimensions are going to be is from here to here. Okay, so I'm going to blow that triangle in here up a little bit. So it's this triangle right here. Because let's read what it says. It says a small 2-person boat is being pulled toward a dock by a person. Here's my person. All right. Hauling in a rope attached to the bow of the boat and run through a ring on the post. Here's the ring mounted at a dock. The ring at the top portion of the post is 6 feet above the level of the bow of the boat. Okay, so if you kind of blow this up a little bit. Okay, this vertical height is 6 feet. Okay, 6 feet above the level of the bow of the boat, the rope is hauled in at a rate of 1.5 feet per second. All right, so if you look at this and you wanted to call this R, right, then dr dt would be equal to 1.5 feet per second, right? How fast is the boat approaching the dock when 10 feet of rope is left between the boat and the ring? So this is going to be 10 feet here at some snapshot in time. And the question about how fast is it approaching is actually this measurement right here. So if you considered that x, that would be dx dt, right? If you said this was x, it's looking for dx dt. Okay? Now, when you set this up, right, you need some sort of, sometimes it's nice to draw a specific picture that sort of relates everything together so that you can kind of get your bearing on what's going on. But when you set this up, you're going to use the same relationship that you used in the first part video for the sliding ladder. It's the same relationship. The two cars, right, the two cars that were driving away from each other use this same relationship. This is a very common relationship for anything that looks like it's got a right angle in it. So you might want to kind of keep that thought in mind. All right. So now we're going to think about this a minute and go, I guess I should take the time derivative. Now I want to take the time derivative and then I want to talk to you about something. So you take the time derivative of this and then I'm going to do it and then I'm going to talk to you about something and I'm thinking we're going to be able to get rid of something. All right, but you go ahead and take the time derivative and turn the video back on. Okay, so you'd have the 2, you'd have the x, and take 1 off the power and loop back in and take the derivative of the inside, right? And you'd have the 2, you'd have the y, take 1 off the power, loop back in and take the derivative of the inside with respect to t. And you'd bring down the power, leave the r alone, take 1 off the power, loop back in and take the derivative with respect to t. Now that is, truthfully, the derivative of this equation right here. Okay, nothing wrong with it. But if you remember, if you notice on your way by, there's something that's going to help us out, okay? Because this 6-foot measurement right here, assuming there's not these waves and the, boats doing this, okay? So they actually have to be considering this like ultra smooth, no wave. Even lakes have a little bit of a bobble to them. But they're saying that this distance between the bow of the boat and where this ring is constant. So this y is actually 6 squared, or 36. So when you take the derivative of 36 with respect to t, it's going to be 0. And this term is going to run to 0. The other way you know that is because, okay, let's say that you left this in and you said, well, here's a 2 and y is 6 feet, right? But what's the change of y with respect to time? It's not changing, okay? Now, again, like I said in the last video, these are story problems. These are not real life problems necessarily, okay? So if you go sailing and you regularly haul a boat in or something, there may be a lot of things that that these stories do not incorporate. That's why they call them story problems, okay? Not factual problems. So one way or the other, the derivative of this term is going to zero out, right? So what you have, and these 2's can cancel out, right? So what you're going to end up with is x dx dt is equal to r dr dt. So it's not so bad after all, right? Very common problem. I can't tell you how many books I've seen with one of these versions on there. All right. Now, let's see if there's anything that we need to know. Okay. I need to know x at this point in time. I know this is 6. I know this is 6. I know at this instant of time this is 10, but I don't know what x is. Can you figure out what x is? Sure, because we keep using this Pythagorean's theorem. Okay, so x squared is equal to 100 minus 36. It's equal to 64. X is 8. So x is 8 feet, right? So x is 8 feet. Okay, dx dt. It says, how fast is the boat approaching the dock? So this is what we're looking for. That's what you're trying to solve for. So dx dt is what you don't know you're trying to discover. R would be the distance from here to here, and they say, how fast is this happening when there's 10 feet of rope left? So R is 10. Okay. And the boat is being hauled in at a rate of 1.5 feet per second, right? So when you solve for dx dt, you get 1.875 feet per second. Okay? All right. Now, sometimes, and I'm not going to set this up, this is going to be a problem for you on the extra problems. Remember, in the description section underneath each video, there are links to practice problems, except for the ones that are proofs. There's links to practice problems, and so in the end of this video, there'll be some practice problems. And so let's think about it. But what you have sometimes is they'll ask you about what this angle is. And what you can do is to set it up in terms of cosine theta or sine theta, right? And when you take the derivative, let's say you use cosine theta. So cosine theta would be, if theta's up here, cosine theta would be this value here, the adjacent side, which is y, right, over the hypotenuse, which is r. So cosine theta would be y over r, right? And so when you take the derivative of this, then you would have minus sine theta d theta dt. So I'm just going to save you a little bit of pain. All right, so go and look at the practice problems. Okay, try a few of these. Go back and look at all these. But, I know a lot of students struggle with related rates. But remember and I think part of the trouble is all of this information is coming in and you don't know where to put it, right? So remember, there's a generic relationship, and then there's this snapshot in time. So sometimes this snapshot here, you have to use it to come up with another piece of information, all right? But you need a generic type of an equation to get started so that you can get all these bits and pieces. And then the specific fills into the exact spots where they're required, right? So there's actually kind of two problems woven into each other. The generic one with just a bunch of variables, maybe a number or two if something's a constant, and then the specific, okay, and at this exact instant in time, we take a snapshot, we freeze it, and then we measure everything, and then we're going to put those numbers in. Okay? So don't forget, like the video if this is helpful to you, or subscribe to the channel, and then look down in the description section for a link to some basic problems. Talk to you later.